Good morning, ladies and gentlemen. Welcome here at the Technical Forum at the group exhibit Hydrogen, Fuel Cells and Batteries. We are kicking off our first session here in the Technical Forum regarding automotive single cells. For that, I invite you all to come, relax here, have a seat and enjoy our next presentation. My name is Mona and I'll be your moderator for the next 20 minutes. So please come and have a coffee. It's all on the house. I'll now announce to you the next topic, which is spatially resolved testing of automotive single cells. And for that, please welcome with me on stage the head of Department Fuel Cell System of the Fraunhofer Institute for Solar Energy Systems, Mr. Ulf Groos. Big hands, please.
Thank you very much. Good morning, ladies and gentlemen. Yes, I would like to talk about the spatially resolved characterization of automotive single cells. Please let me introduce my department very briefly. So we are working directly together with industry. So our business model is to assist industry in their developments and in their market approach. Our main focus areas are, like my talk, looking at the local effects on a cell level and on a stack level. Then we do lifetime testing of components of single cells and stacks and of course systems. We have a broad competence on investigation of contamination effects, whether it's air pollution or it's hydrogen contamination or it might be corrosion effects that occur in a fuel cell system. We do climate testing and we are testing peripheral elements, so to assure system reliability, then you have to guarantee that your valves and humidifiers and so on work properly over the whole lifetime. And last but not least, we of course do also developments on our own, on a cell level, on a stack level and on a system level. So now to give you a motivation, we really would like to see fuel cells on the road and on the streets and that everybody uses a fuel cell. So what do we do as a research institute to help industry? So if industry wants to reduce costs of a fuel cell system, then you have to simplify designs and simplify system architecture. But when you simplify your system, your cell design, for example, then you really have to understand what effects does this simpler design and maybe more cost-effective design has on performance and on lifetime. And this is what I would like to talk about. So if you look at a fuel cell and a fuel cell design, you have your gas inlet ports here and hydrogen or air flows over the active area to the outlet region. So by doing so, we have a reaction inside the fuel cell, and due to the reaction, you have a reduction of the concentration of the fuels because they react, and you have water that is produced over the active area, so relative humidity will rise, and due to the reaction, heat is produced, so the temperature will change also over the active area. So by definition, you will always have inhomogeneities over the active area. And it's very crucial to understand the local effects if you want to optimize your operation strategy or you want to optimize your cell design. I would like to introduce our method, how we investigate these local effects at Fraunhofer ISE. So we get the original bipolar plate design from our customer, and we realize the bipolar plate design in a graphite plate. exactly with the same shape of the channels. And then, as you see here, we segment the bipolar plate. You see here the different segments. Each segment of the bipolar plate is electrically isolated from the neighbored segment. And when we then contact this segment electrically by this, in this case with contact pins, we can draw the current out of the segment and we can sense the potential within each single segment. In schematics, it looks like this. So on one side, we use the original bipolar plate from our customer. Then we have the MEA on top of this bipolar plate, and on top of that we have our segmented fuel cell. The fuel cell bipolar plate, as I said before, has exactly the same shape of the channel structure which is in the original cells. It might be anode or cathode, we don't care. Depends on what you're more interested in when you look at the effects. And on the back side you have the cooling channel structure, which is also exactly the same structure which you have in original. We have here the sensing of the voltage, and then we have the current collector for each segment. The current is drawn out of the cell by this printed circuit board. The setup altogether looks like this. So in the middle part you see our segmented fuel cell here. We have the compression set to get a good contact resistance, and then we have all this cabling. It's for anode and cathode of each segment, and then for the voltage probe. All the cables are connected to the potentiostats. We have 68 potentiostats altogether. 68 potentiostats for 68 segments, so each segment is controlled by its own potentiostat, and the potentiostat has its own frequency response analyzer, its own FRA. In the back you see the gas supply for the single cell. So what can you do with this? And I would like to show some results. In this chart you see a typical polarization curve of our segmented cell. It's in bold lines at different operation conditions, normal, hot and warm up, and we compare it to the results of a single cell or the average cell in a 20 cell stack. These measurements are done on a platform provided by AFCC. It's a generation 3 design. And what we see at the end is that the behavior of the cell in a stack matches exactly with our segmented cell. So what we see in our segmented test cell guarantees that it's the same condition or behavior that we have in a stack. The deviation, at the maximum deviation here at that point from cell in a stack and our segmented test cell is 20 millivolts at 1.5 amps per square centimeter, which is really, really fine. To show schematics of our segmentation, you see all these 68 segments, segment 1 at the inlet and segment 68 at the outlet of the gases. We have a co-flow configuration, and in the next slides I will show you the behavior of different rows. So it's, if you imagine along the channel, we have row 1 at the gas inlet and row 11 at the gas outlet. So now looking at the results of this test cell from AFCC. First of all, I'd like to draw your attention to the cell average, which is shown with these black dots. And then we see the differences of each rows. So we see a huge difference in the cell performance depending on the local spot on the area and along the channel. If we zoom inside, we see at high potentials a picture of the current mapping. So at inlet, we have a very, very low current production. Then current production rises. In the middle area, we have a good current production. And then at outlet area, current production drops again. And in general, the picture keeps along the different potentials. We see at lower potentials that the high current region moves a little bit towards the inlet and then declines slightly to the outlet. But what we see is that in the inlet region, we always have a very low current production. So why is that? And therefore, to analyze this, the electrochemical impedance spectroscopy helps a lot. So I would like to show the high frequency resistance mapping. Now, the HFR, high frequency resistance, gives you a good hint about the membrane humidification and the membrane performance at that point. So what we see is, if we look at all of these pictures at different potentials, what we see is that we have a high HFR at the inlet and also a higher HFR at the outlet, whereas in the middle region of the cell we have a good HFR, which means that we have a dry out or a very dry membrane at the inlet region. We have a good humidified membrane in the middle region of the active area, and then we have a kind of dry out at the outlet region again. And this matches really good with the current production that we have. Within the last months, we did some effort to calibrate the HFR against the relative humidity in the gas channels. So the HFR itself gives you a hint about the conditions of the catalyst-coated membrane and especially the membrane itself, whereas the relative humidity gives you some insight into the humidity of the gases in the gas channels or in the porous region, porous layers. So, and again, if we correlate the relative humidity against the local spots of the cell, we see that relative humidity at the inlet is relatively low, and then we see that relative humidity rises from inlet to outlet, but in the real outlet region we see a drop of the relative humidity again. So due to current production and to water production along the channel, we see the rise of the relative humidity towards the outlet, which is explained very easily due to the water production in the cell. And this drop at the outlet, this depends very much on the cooling structure that we have in this special cell, where we have a rise of the temperature, but a low current production at the real outlet, as we have seen before. So coming to an end and to my conclusion, we at Fraunhofer EASY, we developed a method for spatially resolved characterization of automotive single cells. And the results that we reached with real automotive cells, I mentioned that we used a cell design from AFCC, and we were also working with the AutoStack Core project and the European AutoStack project. We see that the results that we have in our segmented cell match very well with the stack results. So altogether, our multi-channel characterization system enables first current mapping, but secondly, we also can map the electrochemical impedance in the cell and in a certain local spot. And we are also able to map the relative humidity in the gas channels along the channel. And Putting this all together, it gives you a good insight into your cell design, so you can optimize your cell design, you can optimize your operation strategy, and of course, you can validate your models if you have a single cell model. So, thank you very much for your attention so far. I would like to draw your attention also on my next talks. So I will have a talk on balance of plant components in the afternoon, and tomorrow I will have 2 other talks about stack characterization and the in situ characterization of single cells and its components of a single cell. And last but not least, all of you are heartily invited to join us for a good cup of Freiburg coffee at our booth. Our booth is right over there, C62, so you're welcome. Thank you very much.
Thank you very much. I really like the invitation for Freiburg chocolate at booth C62. Are there any questions from the audience at this time?
So you measured the high frequency resistance. If you subtract that off, effectively IR correct your mapping, does that become flat, or are there other losses that are contributing to your decrease in performance at the inlet and outlet?
So, of course, everything depends on each other. The HFR gives you some insights about the membrane humidification, and in this case, it seems to be obvious, and also after discussion with our customer, it is clear that we have a low membrane humidification at inlet, especially, and also at the outlet region. Also, you have to take into account the real flow field design or bipolar plate design, and we know that there might be higher ohmic resistances at inlet and outlet. So if you account or take into account the bipolar plate design, and you see the conditions and conditions of the CCM, then you can explain the current production.
Thank you very much. Unfortunately, we are running out of time. The next speaker is waiting already. But you can take all your questions to the booth, which is C62. Once again, big hands, please, for Mr. Ulf Groos.
Thank you.